Hey folks, I got a quick example of rotational energy. And this dovetails from the stuff we've done earlier, this particular chapter. So let's say I've got this apparatus here. A and B are pulleys. Okay, they're frictionless pulleys, but they do have mass. And we'll call the masses A and B. And we have a larger mass on the left side and a smaller mass on the right side. And we're going to let this system go. Okay. And I want to know when the big mass has fallen some distance h, what's the velocity of the system? And then also, let's find the acceleration of the system as well. Now, in the previous examples, we've done problems like this where you found acceleration by using Newton's second law, net force equals ma, and net torque equals I alpha. But it turns out that you can do the same thing using energy if you let the object fall a distance h. Okay. So we're going to use conservation of energy here. Now, we're going to have changes in height for two of our objects, so we have to establish a zero height. So it doesn't matter where you put it. I'll put the zero height down here. So we'll call that h equals 0. So if you need a moment to copy this down, I'd suggest pausing the video. Okay, so in terms of the big mass, the little mass, the mass of pulley A, the mass of pulley B, the radius of each pulley is r. Let's determine the velocity that the big M attains after falling a distance h. So when I first let the system go, both masses are at a height h. So they're going to have potential energy. So I'll say ug1 plus ug2. Okay. Nothing's moving yet, so there's no kinetic energy. Okay. The pulleys are at a height as well, but their heights are not going to change. So I'm going to ignore their potential energy. It'd be the same on both sides of the equation anyway. On the right side, we're going to have some potential energy. So I'll put ug1 plus ug2. But now everything's moving. So I'm just going to put some of the kinetic energies. All four objects are moving. Two of them are moving linearly, and two of them are rotating. Okay, so there's going to be four terms right there. Okay. All right, now for the details. For the left side of the equation, I've got big M GH plus little m GH. Those are our two potential energies. When the big M is here, its potential energy is 0. The little m will be up here, which will be 2h. So I'll put plus little mg 2h plus. And the next line down, I'm going to write all the kinetic energy terms. All right, so we have the big mass, which is 1/2 mv squared. Plus we have the little mass, which is 1/2 little mv squared. They're going to have the same v. They're all attached. Plus the pulley, which is 1/2 I, I'll put a sub a, omega squared, plus 1/2 b, so I sub b, omega squared. Okay, so there's our big long equation. Okay, so next step, I am going to put in what I for a disk is. A disk or cylinder has a moment of inertia about its center, and these are spinning about their centers. The moment of inertia is 1/2 mr squared. For m, I'm either going to put an a or a b, depending on which one I'm looking at. So on the left side, and then while I'm at it, I'm going to move this over to here. So then I get big M GH, and then this becomes minus little m GH, okay, equals 1/2 mv squared plus 1/2 little m v squared plus. Now I'm going to make two substitutions here. The moment of inertia will be 1/2 times the mass, which we're going to call a, times r squared. And omega is equal to v over r because these ropes are passing over the rims of the pulleys. So I'm going to make all those substitutions in here. So we get 1/2 times 1/2 ar squared times v squared over r squared plus 1/2 I of b, which is br squared, okay, times v squared over r squared. So we made a whole bunch of substitutions there. Now check it out, okay? We can cancel a bunch of stuff out. All the r's are going to drop out. So we'll start with that. Okay, on the left side, I'll go ahead and factor my GH out. And then you get big M minus little m. On the right side, okay, I'm going to factor a quarter out of everything. I'm just going to try to make my math a little easier. So out of everything. So this will become 2 big M V squared plus 2 little m V squared plus A V squared plus B V squared. Okay, so now I've left physics and I am doing algebra. Okay, so I'm trying to solve for V. So I can pull that out. We've got big M minus little m equals, this will be V squared over 4 times 2 big M plus 2 little m plus A plus B. And then I can get V. V is going to be a square root. And we have a pretty big expression here. It's going to be 4 GH, pardon me. So 4GH times big M minus little m divided by, okay, all this stuff here. So we've got a 2 big M plus a 2 little m plus an A plus a B. Okay, so there is the final velocity of the two masses when the big mass starting from rest has fallen a distance h. Okay, now the other thing I asked you for is what's the acceleration? Okay, so what I would do is now I would use kinematics. I would look at this part of the motion for the big mass, and I would simply use v final squared equals v naught squared plus 2a delta x. V final we know, that's what we just calculated. If I square that, you'd get 4gh times the big M minus the little m over that whole thing in the bottom, 2 big M plus 2 little m plus A plus B. Okay, this started from rest, and then we got 2A, and delta x is simply h. And if you solve this for A, well, the h drops out, which is kind of nice. And you divide everything by 2, and you put a 2, or basically make this a 2, and there's your answer. So A would be this, okay? Now, we could have gotten that acceleration using net torque equals I alpha for the 2 pulleys, and net force equals MA for the 2 masses, and we would have had 4 equations of motion. If you add them all up, you would eventually get this equation for A. So when you're trying to determine acceleration, you can use either energy or net force and net torque dynamics. So either one's okay. Also, obviously, be kind of careful on your math. So I hope that example was helpful, and thank you very much.